OK, so I'm going to talk to you today about a competition that I helped to run in 2016. We were emulating, in some sense, the machine learning crowd that does a ton of, competitions like the famous Kaggle competitions within causal inference. And I'll let you know a little bit, in the 20 minutes about how that went, what our results were, and what we learned from doing that. Seriously? Oh, OK. How do I go back? All right. Yeah, seriously. Badass rate points going down by the second. OK, causal inference is hard. I know that sounds whiny. That's OK. I'm kind of used to it. Why is causal inference hard? Because unlike so many fields, like in machine learning, often you can have training data, test data. You know how well you're doing by comparing how you do once you've built a model on your training data by applying it to the test data. Nothing like that exists in causal inference, right? We have missing counterfactuals. What we don't know is the world that we didn't see. So unless you are able to jump between alternate universes or go back in time, it's really hard to figure out what the truth was. So we had to make all kinds of adjustments because of that in the design. But in general, in causal inference, you've got two main sets of choices. One is run a randomized experiment. That's the gold standard. That's what you're supposed to do. But there are lots of situations where ethically, logistically, et cetera, you can't do that. I don't need to stand at the mic, do I? Because I've got a, can you hear me? OK, so randomized experiments, great, often can't do them. So then what do? Observational studies. So that's the bulk of what people do and what the literature is about. Because yes, there's some statistical literature about randomized experiments, but it's just an easier task, right? So when we're in the world of observational studies, we don't have a randomized experiment. The whole name of the game is accounting for your covariates. OK, so what does it mean to account for your covariates? Well, the biggest problem there is you probably haven't measured them all, right? So being able to say that I've measured all confounders, everything that predicts both my treatment and my outcome, it's pretty hard to ever say that that happened, right? So we punted on that. That is not part of this competition. That's something that's not a lot of part of the literature, frankly. And I'm happy to talk to anyone about it. I have done some work in that area, but that's not about today. So instead, what we focused on as the second part was usually what people do is say, let's just control for everything we can. Let's measure as much as we can. Let's control for as much as we can. That's great. But once you do that, it gets harder and harder to build models that you actually believe. OK, so sorry. The competition, because of that, focused on this part of it, the parametric assumptions. OK, so how do we build a model? This is, for anyone who's seen me give a talk, you've seen this slide. So I apologize, but most of this crowd is somewhat new to me, so hopefully I won't be boring you too much. Here's causal inference in one slide. I've got a bunch of observations that received a treatment in red. I've got a bunch of observations that did not receive the treatment in blue. I've got one confounder in this case. So I've set up a really simple situation where there's only one thing that predicts whether or not I got the treatment. And it also predicts the outcome. OK? So that's great. And that's your pretest score, and it's on the x-axis. So what are the solid lines are the true relationship between that confounder and my outcome, which is a post-test. The whole, don't use regression to do causal inference, correlation is not causation, it's a little misleading. Because actually, if you can get that model right, you can do causal inference, right? You actually, if you know you've got one confounder, and you can fit the right model, game on. You're doing well. The problem is, usually more the first part. We don't know we have all the confounders. And then the second part, it can be hard to model. So what's the hard to model piece of it? Well, that's the fact that here we've got something that's not going to fit well, say, with a linear regression. This is why we should be beating up on regression for causal inference, right? Because it's just not the right model a lot of the time. So here, the true response surfaces, as you see, are curved. You fit something linear to that, it's not going to do well. In particular, it's not going to do well here because I don't have overlap, perfect overlap between the two groups, right? So you notice the controls are hanging out down here with low pretest scores. The treated are up here with higher pretest scores. So then the model just wants to extrapolate into that area of the covariate space where I don't have a lot of information. So another way of thinking about that is that for these controls, I don't really have people who look like them. I don't have empirical counterfactuals. I've got no one over here saying, what would have happened to me if I'd gotten the treatment? And the same for the treated over on the right-hand side. I don't have controls who look like them, who can give me information about what would have happened had I not gotten the treatment. And that's the whole name of the game. We need evidence on both sides. We need to be able to think for each person about that alternate universe, right? So we're missing the alternate universe here. OK, so there's two pieces here. There's this overlap piece, and then there's this fitting curves is hard. Now, fitting curves isn't that hard in one dimension. But what about 20, 40, 50, 200, 2,000 dimensions, right? It gets harder. Then again, we have all these tools now for flexible inference that didn't exist or couldn't really be implemented well 20 years ago when, say, propensity scores were being developed. Now we've got them. So if you've heard about propensity scores, it's all about this. It doesn't solve your I haven't measured all the confounders problem. Great tool in a lot of ways, in particular because it lets you see where you don't have overlap. But it's only solving this problem. It's not solving the hard problem, OK? Likewise, all the other methods I'll be talking about today are in that same realm. OK, so there's been an explosion of methods. The vast majority of literature in causal inference and statistics in the past 20, 30 years has been about solving that problem, believe it or not. So all those matching methods, weighting methods, subclassification, that's all about that. More recently, I'd say in the past 10 years, there have been more semi and non-parametric methods. And moving on to kind of combinations of all of these things and ensemble methods, say like the superlearner, which I'll talk about a little later. OK, so wait, before I get there. Again, the competition. Part of what we were thinking about was, OK, there's a whole literature. There's a million methods out there. There's a whole literature. Why is it so hard to figure out what to use? Or how does the typical researcher decide, OK, for my problem? Well, usually, you know what? It's about your field and the journal you like to submit to and what they want to see, which is a pretty crappy way of deciding, right? So what about science? How should we be thinking about how methods get developed and how we evaluate them fairly? So we wanted to create a level testing ground. So this is what we saw in the literature. Most papers only compare a few methods. Methods where if there's no difference between methods, no one's showing you that, right? Because null comparisons are anathema. And there's a bias towards, shockingly, given the incentives in academia and beyond, there's a bias towards your own method. Like, I want to show simulations that make my method look good, right? And if I kind of inexpertly, implement the competition method, oh, well, it's not my method. How was I to know that I didn't choose the tuning parameters correctly or I really didn't do it justice? And I'm not saying anyone's being Machiavellian. Some people may be being Machiavellian. Most people are not being Machiavellian about it. But the incentives to do it right and to be really fair and to actually move towards the truth are not really there. Oh, there's a typo. Cocoise. And you also might only choose evaluation methods, metrics that favor your method, right? Again, are you thinking it through that way? Are you doing that explicitly or not? It doesn't almost matter, right? And then calibration to real life. So because of this challenge I said before, but there's no real data set where we know the truth. There are some things, constructed observational studies, that lean in that direction. But in general, that doesn't exist. We often are simulating. How do we create simulations that look like real life and real data? That's really hard to do. And I'm not saying we change the world on that, but we tried to stick in that direction. Okay, so how did we do it? We crowdsourced submissions, right? That's what a competition does. Send me your best method. You implement it. You think this is a great method? You tell me how to implement it, right? Or you implement it yourself. We had 2 different versions. We're reporting everything, and we're putting all the data out there and all the code so that anyone can go back and use it and try out and see. Fair comparisons, we really tried to incorporate a number of metrics that would evaluate the strengths and weaknesses of different methods. And we started, at least, with covariate data from a real study in an effort to try to calibrate towards real life. So all the covariate data is real, and then we simulated treatment and outcomes so that we would be able to learn about, for this kind of, the idea in our heads was, if we have this kind of assignment mechanism, maybe this kind of method does well. Or if our response surface looks like this, maybe this kind of method. It turns out we did not learn that. It was hard. OK, so timeline, boring. About 15 do-it-yourself. I'll tell about those differences in a second. And submissions and about 15 black box submissions. OK, we assume ignorability throughout. What does that mean? It means we assumed throughout that the researcher had all the covariates they needed to do causal inference. So we got rid of that, the hard problem. Okay, there's no confounding if you control for the right set of covariates, which is a subset of the covariates we hand you. Calibrated to real life, I just talked about that. We simulated treatment and assignments, so we knew what the mechanisms were. The goal was to estimate the sample average ooh, that's not right. It's SAT. Sample average effect of the treatment on the treated. Sorry, that should say SAT. I'm going to talk about the simulation knobs in a second, and we had 2 versions, do-it-yourself and black box. Here are the simulation knobs. Degree of nonlinearity. So I showed you a picture of something nonlinear before. Now we've got nonlinearity in roughly, somewhere between 10 and 50 dimensional space, depending on the setup. We did that in any of a variety of different ways: step functions, exponentiating things, et cetera, et cetera. Percent of treated, where sometimes some methods don't do well when there aren't more controls than treated. So we varied that. It was either 1/3, 2/3, or the opposite. Overlap balance, that was another feature I showed you in the plot before. If you don't have a lot of observations that overlap with each other, it gets harder. Alignment, that has to do with the fact that maybe you have 50 covariates, and maybe 15 of them predict the treatment, and 20 of them predict the response, but only 5 predict both. In that case, only 5 are confounders. And methods vary a lot in how good they are at figuring that out. And if you work really hard to, for instance, if you're propensity score matching, to balance all the things that predict the treatment, that's not necessarily the best thing for your treatment effect estimation, because you may be ignoring important covariates for the outcome. And treatment effect heterogeneity. I think we had 1 setting where everyone had the same treatment effect, and beyond that, it was like the picture where there's a lot of heterogeneity. OK, then 2 different competitions. One with 7,700 data sets. We have 77 settings that varied levels of that knob. Each setting had 100 different manifestations. Then people sent us methods that had to take a certain kind of input and output something very specific. And boom, we went to town with that. The other version was we handed out 20 data sets. For people who really believe this is an art form, I need to do it myself, I need to be intimate with the data and thinking about it, et cetera, we gave out 20 data sets to do that. So I'm going to focus less on that part of the competition because it's harder to make any strong conclusions with 20 data sets. OK. So here's a brief summary of the winners. We did give out gold medals. They were gold-covered plastic medals, really. But people, I think, felt good about the medals that they got. But in some sense, we didn't really feel comfortable at the end of the day saying that there were real winners, because they all kind of, some things that were good at this weren't good at that, et cetera. But overall, if you really pushed us, the winners were ones that flexibly modeled the response surface, right? Which is new. This has not been emphasized in causal inference in the past 30 years. Everything has been about modeling the treatment assignment, things like the propensity score. In part because, again, there weren't these fancy methods until recently that could do the other part well. So ones that really focused on the expectation of the outcome, conditional on treatment and covariates, were the ones that kicked ass at the end of the day. And those could have used a variety of things to do that flexible model fitting, from BART, random forest, Gaussian processes, and often ensembles thereof. Okay. Because at the end of the day, we were having a hard time learning about what actually is the feature that makes a difference, and we couldn't really learn that from our evaluation. It was very noisy. It was really hard to find settings where one method really dominated over the others. We instead created a bunch of new methods. So it was like, trying to think, there was a toy I used to have when I was little, like Transformers. You could like take the one piece of this and shove it into that, right? You could like make cool hybrids. So it was a fun experiment like that. Let's take this and shove it over here, and so I'll show you a little about those as well. And we learned the most from that process. And it also made me think, isn't that a better way to do science? Where instead of me saying, for instance, like I've written about BART, so BART has to win. It's like, well, what if I take the piece of BART that's good and take the cool thing about superlearn that's good and mash them together? Okay. So here are the people who won medals. The first is called CalCause. It's an ensemble algorithm that uses cross-validation to choose between random forests and Gaussian processes. I will say, though, that it shows random forests 95% of the time. I'm working on Gaussian processes and causal inference right now, and it has a lot of promise, but it's hard to do well automatically. BART is Bayesian additive regression trees. The mean function of BART is a sum of weak learning regression trees, and it avoids overfitting by default prior distributions, kind of like a Bayesian form of boosted regression trees. Superlearner plus TMLE. So this is like the Mark Vanderland camp, for people who know that world. So they had a big ensemble that had a wide, well, actually it wasn't that wide, a library of different options, both to fit the response surface and the assignment mechanism. And then it applied a targeted maximum likelihood estimation adjustment at the end. H2O, by the way, all these things, I don't know about CalCause. These are all sitting in R, and I'm going to give you links later, or names of packages. This is another ensemble. Ensembles, not surprisingly, ensembles get to choose the best among a variety of methods. So the ensembles did really well, except for on computational time, right? So it also chose from among a variety of options. Oh, wow. I'm running out of time. I will say that in the do-it-yourself competition, there was one real standout submission by J.R. Lockwood, which I don't have time to talk about. This is also all in a paper that I'll give you. It's sitting on archive. OK, a bunch of different things we looked at. So I'm going to actually skip, I'm sorry, the do-it-yourself, because it's 20 data sets, and it's sitting in the paper. So it's all out there. Instead, I'm going to show you the 7,700 data sets. So all the dark points, so we've got, bias, are circles, and RMSE, and left-hand axis, RMSE, triangles, and right-hand axis. But in some sense, and everything has been standardized by the standard deviation of the outcomes. So if you're used to thinking in like effect size, standardization, it's like that. So one takeaway is that everything did decently well, or most things did decently well, if you think of like 0.05 as being kind of a reasonably small level of bias. The mashups did better because what? We took a bunch of the good features and put them together for the most part. Here are the winners. And then there are a bunch of other methods that did fine, just not superlative, okay? So we actually didn't learn a lot from that piece. We learned more from this. And I apologize for this because there's no way I'm just going to have to tell you what all these letters mean. But this is interval length versus coverage. So basically, we want things that cover. So we want things over here where you see there's nothing. And we want things up here because we want short intervals. So short intervals that cover is the name of the game. And we don't have a lot of that. So BART did really well with regard to RMSE and bias, but not with coverage. With coverage, it's getting like 83%, 82%. It's got a really short interval. Although when you switch it to have symmetric intervals, which makes no sense from a Bayesian point of view, it does much better. So we're still investigating that. When you add the propensity score as a covariate, it does much better. When you combine it with TMLE, it does great, right? Superlearner, similarly, see that one over there? Didn't do so great coverage-wise in the beginning. When they added BART, boom, they did much better. Actually, that was the Superlearner team who went back and thought, oh, let's throw BART in the library. And they did, and they resubmitted. So we're still learning about the coverage, but that was interesting. I have 0 time, and dinner, rather lunch, is waiting. So I'm going to skip this piece and just go to lessons learned. All right, so the big takeaways for us were that nonlinear response surfaces, not the model for the treatment, but the model for the response was really where the action was, which frankly fits with a lot of theory. Barton random forests, in general, like treed algorithms, were the ones that stood out as standalone, as in non-ensemble algorithms. Coverage was a problem across the board, so we need to think about that. TMLE, I have to say, I was pretty cynical about it before the competition, and now I'm kind of sold. I still don't really understand it because it's super hard. But I'm working more towards doing that and have built packages now that include it by default because it's so helpful. And I will, yes. There's a new competition this year, which the deadline is April 30th. And it's a little tricky. So, but if you Google, well, there's the link, but also if you just Google ACIC, which stands for Atlanta Causal Inference Conference 2018, you will, and challenge, you'll get there. So I want to thank you for attending to this when you can smell the pizza in the background. And I'll just leave this to show you the packages that are sitting on CRAN to highlight a new BART causal one that we're about to put on CRAN. I know I said the same thing a month ago, but that incorporates a lot of the features. A lot of the good things we learned from this are now sitting in there. But it's sitting on GitHub if you want to help us test it out. The competition data is sitting on GitHub. So if you're writing a causal inference paper and you need testing grounds, boom, you've got 7,700 data sets across a wide variety of settings. Use them. And then cite us, of course. And the paper is in its second round of reviews at StatsI, but is sitting on archive. So we'd love comments on it. So thank you very much.